Hello everyone, welcome to my way. Have you ever wondered how tiny RF signals become powerful enough to travel through the air, reach satellites, radar systems, or high-speed communication links? Today, we're talking about solid-state power amplifiers, commonly called SSPAs, and everything you need to know about them. From RF amplifier basics to gain calculations, gallium arsenide versus gallium nitride technology, power amplifiers, low noise amplifiers, and where they're used. Let's get started. An RF amplifier is an electronic device that increases the strength or amplitude of a radio frequency signal while preserving as much of the original information as possible. Think of it like speaking through a microphone connected to a loudspeaker. Your voice stays the same, but it becomes much louder. RF amplifiers perform the same job for radio signals. At my way, two primary amplifier categories are offered. The first is low noise amplifier or LNA. The second is power amplifier or PA, also known as solid state power amplifiers. But what's the difference? Imagine receiving a very weak signal from a satellite located thousands of miles away. That signal may only be a few billionths of a watt. Before processing it, we need to amplify it, but without adding much noise. That's exactly what a low noise amplifier does. It provides higher gain, extremely low added noise, but better receiver sensitivity with improved signal to noise ratio. LNAs are normally placed immediately after the receiving antenna because any noise added later cannot be removed. Now let's look at the transmit side. Here we already have the information signal. Our goal is to increase the power before sending it to the antenna. That's where the power amplifiers comes into picture. A solid state power amplifier boosts the RF signal to the desired output power while maintaining good efficiency and linearity. Higher output power means longer communication distance, better radar detection range, stronger wireless links, higher reliability. SSPAs are also used as driver amplifiers for TWTAs, which is traveling wave tube amplifiers. Modern RF amplifiers commonly use MMIC technologies. MMIC stands for Monolithic Microwave Integrated Circuit. Two semiconductor technologies dominate the industry: gallium arsenide or GaAs, gallium nitride or GaN. Each has its own advantages. Let's compare them. Gallium arsenide amplifiers typically offer excellent low noise performance, higher gain, and lower DC power consumption. They're commonly used for low noise amplifiers, driver amplifiers, and medium power microwave amplifiers. Gallium nitride technology has become the preferred choice for many high power systems. Why? Because GaN devices can operate at higher voltages, higher temperatures, higher power density, and have better efficiency. This means more RF power from a smaller package. When selecting an amplifier, engineers usually look at several key specifications. These include frequency range, gain flatness, output power, saturated output power, and 1 dB compression point, input and output VSWR, noise figure, efficiency, harmonic performance, third order intercept, also called as IP3, supply voltage, and current consumption. Each specification tells us something different about amplifier performance. Now let's talk about one of the most important concepts in RF systems, which is gain. Gain simply tells us how much an amplifier increases the strength of a signal. In RF engineering, we don't usually talk in raw power ratios. Instead, we use decibels or dB because it makes system calculations much easier. And the basic relationship is very straightforward. Gain is just output power minus input power. So if you know any two values, you can always find the third. Let's look at a simple example. Suppose we start with input signal of 0 dBm. and we pass it through an amplifier that has 30 dB of gain. Since gain adds directly in dB, the output becomes 30 dB. Now here's something very important that often gets misunderstood. When we say an amplifier has, for example, 30 dB gain, or we calculate an output like 30 dBm or 40 dBm, that does not mean automatically the amplifier can actually deliver that power in a real system, because every amplifier has limits, and this is where two key specifications come into picture: P1 dB compression point and Pset or saturated output power. Let's start with P1 dB, also called 1 dB compression point. In an ideal world, if an amplifier has 30 dB gain, it will maintain that gain perfectly for all input power levels. But in reality, as we increase the input power, the amplifier eventually stops behaving linearly. At a certain point, the gain starts to drop. The point where the gain has dropped by 1 dB from its ideal linear value is called the P1 dB point. So what does that mean practically? It means below P1 dB, amplifier behaves linearly. At P1 dB, gain starts to compress. Above P1 dB, distortion increases significantly. So P1 dB is basically the maximum usable linear output power of the amplifier. Now let's talk about Pset or saturated output power. If we continue increasing input power beyond the linear region, the amplifier eventually reaches a point where it simply cannot provide more output power. This is called saturation. At Pset, the amplifier is fully driven, and no matter how much input you increase, the output power will not increase significantly. Instead, it flattens out. So, Pset is equal to maximum achievable output power. Beyond Pset, there is no useful gain. Now let's connect this back to our earlier calculation we said. Input is equal to minus 10 dBm, gain is equal to 20 dB plus 30 dB, and output is equal to 40 dBm, which is 10 watts. But here is the critical question. Can the amplifier actually support 40 dBm output? The answer depends entirely on its P1 dB and Pset ratings. If the amplifier has P1 dB, which is equal to 30 dBm, and Pset, which is equal to 33 dBm, then trying to push it to 40 dBm output is not realistic. What will actually happen is gain compresses before reaching that level. Signal becomes distorted, output saturates around Pset, and spurious signals and harmonics increase. So even though your math says 40 dBm, the physical amplifier says, I can only safely deliver around 30 to 33 dBm. Now let's take a real RF chain example and actually walk through it the way an RF engineer would think during system design. We'll not just do the math, we will also check whether the amplifiers are operating in the safe linear region or hitting compression. So let's start at the beginning. Our signal generator is producing minus 10 dB. This is a very small RF signal, just enough to represent information but nowhere near transmission level. First stage is a driver amplifier with gain which is equal to 20 dB and P1 dB which is plus 10 dBm. So output becomes minus 10 dBm plus 20 dB which becomes plus 10 dBm. Now we quickly check. We are right at P1 dB. So we are at the edge of the linear operation. Now this signal goes into power amplifier with gain which is equal to 30 dB. Now P1 dB is equal to 38 dBm and Pset is equal to 40 dBm. Ideal output is 10 dBm plus 30 dB which becomes 40 dBm. Now in communication or radar systems, we care about signal quality. So we ask, can we stay linear? Answer it, yes, but only up to P1 dB 38 dBm. But in some systems, linearity is not the main concern. Instead, we want maximum RF power out of the amplifier. So we push toward the saturation. which is PSAT equals 40 dB. Now what happens? Gain compresses, signal distorts, but output power is maximum. So in this case, we operate closer to 39 to 40 dB, which is PSAT region. So the key idea is simple. P1 dB means clean linear operation. PSAT means maximum power operation. And depending on the application, we choose one or the other. Now let's discuss one of the most important linearity specifications, IP3 or third order intercept point. Suppose two signals enter an amplifier. Instead of producing only those two signals, a nonlinear amplifier also generates unwanted frequencies. These unwanted signals are called intermodulation products. If they become too large, they interfere with the nearby communication channels. A high IP3 means better linearity, lower distortion, cleaner transmitted signals, and better receiver performance. IP3 is typically measured using two-tone tests. Two RF signal generators produce closely spaced frequencies. Both signals enter the amplifier. A spectrum analyzer measures the desired output signals and the unwanted third-order products. The greater the separation between the desired signals and the distortion products, the better the amplifier's linearity. The trade-off is reduced linearity, making it well suited for constant enveloped signals rather than complex modulation schemes. Amplifiers are also classified according to their conduction index. Examples include Class A, Class AB, Class B, and Class C. For many RF transmitter applications, Class C operation provides very high efficiency. High-power amplifiers generate significant heat. Without proper cooling, performance can degrade and component life may be reduced. That's why many high-power SSPAs are available with integrated heat sinks, forced air cooling fans, and rugged mechanical housings. Proper thermal management helps ensure reliable long-term operation. Depending on frequency and power level, amplifiers may be offered with different RF interfaces. The choice depends on frequency, power handling, and system integration requirements. Like any precision RF equipment, amplifiers should be handled carefully. Some good practices include: observe proper ESD precautions, never exceed the specified input power, verify correct DC supply voltage before powering on, and ensure proper cooling during operation. Few more: terminate unused RF ports correctly, never operate a high-power amplifier without the proper load or antenna connected, keep connectors clean and properly torqued. Following these simple guidelines helps maximize amplifier life and performance. RF amplifiers are one of the fundamental building blocks of every wireless system. Whether it's a low noise amplifier, helping detect incredibly weak signals, or a solid-state power amplifier, delivering high RF power for transmission, choosing the right amplifier technology and specifications is critical for the system performance. Modern MMIC technologies such as gallium arsenide and gallium nitride continue to push the limits of frequency, efficiency, power, and reliability, making today's RF systems more capable than ever before. If you enjoyed this video, don't forget to like, subscribe, and leave your questions in the comments. Thanks for watching, and we will see you in the next video.